figure this out on the back end. I don't really know why it's not working. Maybe that's just something. I don't know. I can't worry about it. Okay. So let me go ahead and share my screen. View. Okay. All right. So I just tried to start the live stream to YouTube and I got an error message. So I don't know. I got to try to figure out, why it's giving me the error message. So I've been streaming streaming directly to YouTube for like years. So this is the first time it's like giving me this error message. So we'll figure it out on the back end. So I am recording this and I'll just figure out how to make it available after, retroactively. Okay, so greetings, gentlemen. I hope everyone is doing well. We are moving into chapter 2, and we're basically going to be diving deeper into more concepts centered around taking a derivative, right? The main takeaway that we've had for a derivative is that it's the slope of the tangent line at a point, right? I think when we introduced derivative, we kind of introduced it with the limit definition as the second point gets closer and closer to the first. We get a better and better approximation for the slope of a tangent line. And then we had the limit definition. And then we started exploring some techniques for the derivative shortcuts, right? So let's let me see. I'm gonna go with this. And if you have questions, feel free to either unmute yourself or type in the chat. Matter of fact, let me log in here so I can monitor the chat. Let's join. That is correct. Don't connect audio. Turn it off. Okay. Stay as a participant. All right. So it looks good. I'm just going to go with it. All right. Okay. And let's go like this. Okay. So chapter 2 is on exponential and log functions, right? So chapter 1 was all introducing the derivative. So now we're going to look at the derivative when applied to exponential and log functions. Okay. So 2.1, exponential and log functions of natural base E. Graph and solve exponential functions of natural base E, and graph and solve log functions of natural base E. So I think this is kind of a review from like college algebra 2, right? On exponentials and logs. So the natural base denoted E is the value given by the limit as n approaches infinity of this expression, which is 2.71, 82, 81, 82, 84, 5, so on and so on and so on, right? Okay. All right, so if you were to calculate this limit as n approaches infinity, the result gets closer and closer and closer to this number, right? So this is kind of how we find the exponential base E, exponential function base E. And so what we're going to discover is that E has a lot of like unique properties that come out, and why it's isolated in our discussions. We'll get into those details momentarily. So theorem 1, continuous exponential growth. A quantity P is growing continuously at an annual percentage rate R, expressed as a decimal, and has a future value after T years given by this. So this is the future amount based on continuous growth, right? So like if you have an account that's growing continuously, we use this guy. I call this the PERT formula. That's just how I remember. Whenever I see an account is growing with a continuous growth, growing continuously, then I think PERT, this guy, PE to the power of RT. So Lewis invests $5,000 in an account that earns interest at an annual rate of 3.25%. Find the future value of Luis's account after 5 years if the interest is compounded continuously. All right, so continuous compounding is again PERT. Hang on. All right. So this looks like a case where we're going to use PERT. Let's see. So we'll use this guy. The future value is going to be P times E to the RT. Okay. Find the future value after 5 years. So the amount in the account after 5 years, the P is the principal, 5,000. E is a function in the calculator. to the power of the rate is 3.25%. So when we're doing these calculations, we have to express the rate as a decimal. They give it to us in a percent. So if we want to go from percent to decimal, hopefully you're thinking divide by 100. So the decimal is going to be 0.0325. And the number of years is 5 years. And usually the time is expressed in years. Okay, so I think everything we just evaluate, right? We have all variables are accounted for, so we just plug in. Let me use my calculator. Actually, this right here. Need to reload it probably. Okay. It's gonna be one of these. This one. This one. Okay, let's try this one. This one. This one, there it is. Reload. Let's try refreshing this. Okay. And then we're gonna pull this guy over here. Okay. I don't know, everything is kind of lagging today. So our goal for today is sections to complete sections 2.1 and 2.2. Let me see the time. 20 minutes. Hey Google, set a timer for 20 minutes.
All right, 20 minutes, starting now.
All right, so I'm just gonna put this in the calculator, 5,000 e, I'm gonna hit second natural log, so e to the power of 0.0325 times 5, close parentheses, okay? So in the account, he starts with 5,000. After 5 years, it should be 5882.24. Okay. So 5882.24. Okay. Quick checks I'm going to leave for you all. We have a definition. So for any positive number x, the natural log or log base e of x is given by ln. The x is going to be log base e of x. The equation y equals natural log of x is equivalent to e to the power of y equals x. Okay. So natural log. So we just kind of we introduced exponential, right? E to the power of x. So then we're defining the natural log as log base e of x, right? So whenever you see natural log, it's the same as log base e. Sometimes we do need to do this conversion, right? I just want you to be aware that natural log it just means common log base e. If no base is written, right? If there's no base written, then there's an implied 10. And then from college algebra 2, right? If we wanted to write a log exponential form, so if we have the equation y equals the natural log of x, we just said that natural log is common log base e. So this is the same as y equals common log base e of x, like that. So that's a log of x base e. So then from college algebra 2, if we want to write this log as an exponential, we would take the base of the log, swing it to the other side, it becomes the base of the exponent. I'll continue over here. So then we'll have, that'll give us e to the y equals x, right? So this is the exponential form of that log function, okay, which is what we have over here. Okay. All right. So find each of the following. If necessary, use a calculator to approximate the values to 3 decimal places. All right, so for A, natural log and E, they're inverses of each other. They cancel each other out. So essentially this 4 just comes down. Whenever we take the log of a power, the power can come down. And again, natural log and E are inverses of each other. So the only thing that's left there is 4. The natural log of 1 in general, the natural log of 1 is 0. And also the log of 1 is 0. So that guy should just be 0. Okay. Again, for C, natural log and E cancel each other. The log of a power, when we take the log of a power, that allows us to bring the power down in front. So that guy should just be -1. The natural log of 20, I think we would need to use our calculator. Three decimal places. So 2.996. Okay, now when it comes to like doing these calculations in like Pearson, be sure to keep your answers exact to the very end. So when we start working these longer examples or questions or equations, whenever you have to, if you crunch a number along the way and you're going to use the decimal, you got to write out the long decimal every time until you get to the end. And then once you get to the end of the example, that's the only time you round is at the end. If you round along the way, it's going to make your final answer more and more skewed, and your chances of getting it right are low. All right. So either you crunch the number and write out the long decimal every time, or you just keep it exact until the very end. So that's just a common error that's a common challenge that students tend to have. I just want you to kind of be aware of. 4, 0, -1, and 2.996. Okay. Give me just a moment. Okay. So we have this theorem 2, properties of natural logs. So property number 1, the natural log of a product is the same as the sum of the logs. All right, so that's pretty much it. Property number 2, the log of a quotient is the difference of the logs. So the first one is the product rule, second is the quotient rule, third one is the power rule. The log of a power is the power times the log. So again, this allows us the power when we take the log of a power, that allows us to bring the power in front in this fashion. Again, natural log and E are inverses of each other. So the natural log of E is 1. Properties 1, 2, and 3 require that M and N are positive. In general, the log of 1 is 0. Okay. Okay, so this is the change of base. So property 6 is called the change of base formula. When we have the log of M base B, that's going to be the same as the log of M divided by the log of B. And the log of M, the natural log of M, let me see. Actually, I think that's an error. That looks like an error. If there's an error there, that's not right. Let me fix this. Okay, so I'm gonna strike through this. I think this is incorrect. Give me just a moment. So ways that we can correct this. right? So if this were the log base b of m, then it would be true, right? And I'll say or if it had, if we started with the natural log of m, that's the same as what? The log base e of m. So then you could do the log of m divided by the log of e. You could do the log of m over the log of e. But I think what they really intended was the part in red. That's why I was kind of pausing. Like there's a couple of ways that you can make that correct, but what was written was not correct. You can either change the left to make it correct or change the right to make it correct. But I think they intended a different expression on the left. All right, because the original thing, log base b of m, you can write it as log of m, natural log of m divided by natural log of b. You could also write it as the log of m divided by the log of b. If they did the natural log of m, that would be, you can write that as the log of m divided by the log of e. Yeah. Anyway, so the red or the purple, that'll kind of sink in. You know, it's not as bad as it looked. I really think they intended the red. I just offered the purple as an alternative, but I really think they intended the red. So then the natural log of e to the x, again, we take the log of a power that allows us to bring the power in front, and natural log of e cancel each other. So it's like x times 1, which is just x. Again, e to the power of natural log, they're inverse of each other. They cancel each other out. So what's left there is x as well for all x positives. Okay. So given that the natural log of 2 is this and the natural log of 3 is this, use the properties of natural logs to find each of the following. Okay. So, okay. So the first one, we have the natural log of 6, right? So that one, 6 is what the same as 2 times 3. So that's going to be the same as natural log of 2 times 3. Now, one of the properties we just showcased was the product rule. The log of a product is the sum of the logs. So this is the same as the natural log of 2 plus the natural log of 3. Okay, so we can just add those two results together. I'm kind of running short on space. Let me see. 1, 2, 3, 4. 1, 2, 3, 4. So that's a 7. Okay. 1, carry the 1. 10, 9, carry the 1. So that's a 7, and then a 1. Uh, 81 is what, 9 squared? So this is the same as, so if 81 is 9 squared, we can apply the power rule. So that would be the natural log of 9 squared. Let me just write it. I was going to do it audibly, but for the sake of simplicity, right? I was trying to save on space. So when we take the natural log of 9 squared, we can apply the power rule. This allows us, honestly, I think we say 3 to the power of 4, because it's 3 squared squared. So let me take it a step further. 3 to the power of 4, right? So then this is going to be the same as 4 times the natural log of 3. So there's going to be 4 times that result at the top. Let me see. Times 4 is 4, carry the 2. 32, 34, carry the 3. 36, 39, carry the 3. 3, 4. I think this is it. Again, I'm just practicing mental math. You can use a calculator for this part. The main takeaway is applying the properties and then just use your calculator. So in part C, we have the natural log of a quotient. So the log of a quotient is the difference of logs. So this is going to be the same as the natural log of 1 minus the natural log of 3. Natural log of 1 is 0. Natural log of 3 is given. So then the final result should be this guy. Okay. Okay, so we have several properties at play in part D. First, we're going to apply the product rule. The log over product is the sum of the logs. So this, we can rewrite this as the natural log of 2 plus the natural log of e to the power of 5. Let me just a moment again. Okay, so natural log of e, well, natural log of 2 is given. We can apply the power rule for that second term, so that this allows us to bring the power down. So that's going to be 5 times 1, which is just 5. So 5 plus the natural log of 2. So then it looks like that result is 5.6931. Okay. Okay. So then for part E, we have to apply what's called the change of base formula. Let me minimize this. So this is the same as okay, we should be able to do the natural log of 3 over the natural log of 2. I was about to do the log of 3 divided by the log of 2, but then we would have to do change of base again to get it into a log form, the natural log form. So we should be able to just jump straight into the natural log form, right? Log of 3 base 2 is the same as log of 3, natural log of 3 divided by natural log of 2. That's also the same as common log of 3 divided by the common log of 2. So with the change of base, you can use either natural log or common log as long as you're consistent, okay? And I think these two are given. We just have to divide them out. Hey, Google, what's 1.0986 divided by 0.6931?
1.098 divided by
Nope.
0.693 is approximately 1.58.
She didn't get the whole thing. 1.0986 divided by 6931. This is like 1.585. Okay. Let's see. 1.7917, 4.3944, negative 1.0986, 6931. I think we're good. 5851. Okay, that's fine. Okay, so we have this theorem. We say the natural log of x exists only for positive numbers x. So the domain of the natural log is a positive real number, 0 to infinity. Natural log of x is negative when x is between 0 and 1. It's equal to 0 when x is 1, and the natural log of x is positive when x is strictly greater than 1. So again, this is basically, just describing the domain and range. I like how the function is behaving from the graph. So the graph of the log function, if you consider the xy plane, it has a vertical asymptote on the y-axis, and then our graph starts infinitesimally close to the y-axis, but slightly to the right, and it's coming up nearly vertical along that vertical asymptote of the y-axis. It passes through the point 1, 0, and then kind of veers off to the right. All right, so that's where this is coming from, talking about how the function is behaving on these different intervals, the graph, right? Okay, so again, in general, we can only take the natural log of positive numbers. So then, long story short, this 5. I don't even know what's going on. So again, we can only take the log of positive numbers. So this 5 minus 2x has to be strictly greater than 0. Okay. So then 5 is greater than 2x. So then 5 over 2 is strictly greater than x. All right. So then these are the numbers going from negative infinity up to 5 over 2. Infinity always gets parentheses. Again, there's no bar, so this will get parentheses as well. Okay. Say we get a result like this, and you want to kind of test it to make sure it's correct. We can just choose several values. Like for instance, zero is in this domain. So when x is 0, we should get a true result. So the natural log of 5, there's going to be some positive real number, right? But if we were to choose something like what, number 3, if we let x be 3, we should get something that's false, right? So if we plug in 3, we're going to have 2 times 3 is 6. 5 minus 6 is going to be -1, and we can't take the log of negative numbers, right? So we can choose several values that should make it true and test to make sure it works. We can choose several values of x that make it false, just to make sure that that lines up as well. And that's about the best we can do there. Okay, I think my alarm should be about going off soon. Let me just kind of scan. Solve the following exponential equation using logarithms. I kind of want to do these. I'm going to go ahead and do this. Let's see. 3 decimal places. Okay. So then for part A, so we can take the natural log on both sides, right? To get the variable out of the power, take the natural log here. This allows this to come down, and take the natural log of this guy. Okay. So then on the left we would have 3x. On the right we would be left with the natural log of 2. Ultimately, x equals the natural log of 2 divided by 3. And then from there we just use our calculator. Hey Google, stop. 3 decimal places. So 231. Approximately 231. Okay. So then let's work on part B. Okay, so I'm tempted to go ahead and take the log on both sides. But I'd rather isolate that exponential expression first. So I'm going to divide both sides by 250 first before I take the log. So then when I divide both sides by 250, on the left I just have this part. And on the right, what is that, a 3? So now when we take the natural log on both sides, again, that allows this power to come out in front. So on the left, we have this 0.015t. On the right, I'm just going to leave it as the natural log of 3, right? So if you were calculating this, and if you put in your calculator a natural log of 3, you get a decimal. This would be one of those moments where you need to write out the long decimal. If you don't leave it as the natural log of 3, you got to write out the long decimal. Otherwise, it's going to make your fine line some more and more askew, and then you're going to see the challenge like when you're going through the quizzes and the exams on Pearson. Okay. So I tend to leave it exact until the end. So then now we have that t equals the natural log of 3 divided by that decimal. Man, I cannot get my typing together. I'm gonna just redo both. Okay. 241, 73.241. So again, if you have questions, feel free to either unmute yourself or type in the chat. Let me check the chat real quick. Okay, so the Q&A in the chat look good. Let me see, 231, 241. 231, 241 is fine. Okay. All right, let me kind of scan. We got about 10 slots left in this section. Exponential growth rate expressed as a decimal and a doubling time. Okay. Doubling time. I don't know who that is. I'm gonna have to wait because I'm in class. So I tend to just use the rate times time. Yeah, the first one. The doubling time. Actually, I kind of flow between. I'll either use the first one or the last one. The doubling time equals the natural log of 2 divided by r. Yeah, I'm gonna have to chill. Let me see. So I'm gonna have to leave this one as an exercise. It's not. It shouldn't be too terribly bad. Oh, I totally want to do this one. Is this the last one? Example 7. Okay. Yeah. Let me showcase this one. So solve. I mean, even though we're kind of a little bit pressed for time, so I want to solve this this log equation. So I'm going to subtract 5 from both sides. I want to isolate my log, right? So I got this 7 natural log of x plus 3. Subtract 5 from both sides. What is that? 14. Then we can divide both sides by 7. So then on the left, we have this natural log of x plus 3. On the right, we have 2. Okay. So now we've isolated the log. So then to clear out the log, we say we raise both sides to the power. We say e to the power of both sides. So we're going to say e to that power and then e squared. So then on the left-hand side, e and natural log cancel each other. So on the left, we're left with x plus 3. And on the right, we have e squared. So then x equals e squared minus 3. That's the exact result. And we use a calculator to get that approximation. Okay. 3891. Wasn't too bad. 3891 is fine. Okay. So we have a typed version of what we just experienced. So again, I'll make a copy of this available at the end of class momentarily. So I'm gonna go ahead and hop into the next section. Okay, that's a pretty decent review of that section. It's a good idea to look into that. Okay, so that was 2-1. So now we're starting the derivatives of natural log, of exponential and log functions. Okay, so let's change this view. Single page. Okay. All right. Let's see. This is a little bit better. Okay, so continuing chapter 2. So again, here we're looking at section 2.2, derivatives of exponential base e. All right, guys. So again, I just want to remind you that attendance is being recorded automatically, and what that means is that it just logs when you guys show up and when you leave. So I mean, I'm seeing the notifications of when people are showing up, when people are leaving. I'm just letting you know that on my end, if I notice that it becomes excessive, then I'm going to start docking people. If you start getting docked for attendance, either being late or unexcused absences and things of that nature, then you could be booted and you may or may not be able to get back in. As long as it's not excessive, then I don't usually make a big deal about it. But if I notice that people aren't, and I try to be easy. Again, just show up and send out and just listen. I don't make a big deal about other stuff, right? As best you can. But for right now, I'm gonna still be kind of easy, but just be careful with that. Just want to kind of give you a heads up. Okay. So let me see. Algebra 2. Yeah, guys, you can't be missing, man. He's in my next class, and their constraints are even more tight than you all, but it's fine. Okay, so section 2.2, derivatives of exponential. I think that stuff is due. It's we've already discussed this. Like, 2.2 derivatives of exponential base e functions. Okay, so the derivatives of the exponent. Okay, so a few objectives here. One, differentiate the exponential base e functions, and two, solve applied problems involving exponential base e functions and their derivatives. All right, so we have the derivative of the function f. F of x given by f of x equals e to the x is itself, right? So because of that property, right, of exponential functions, that's why it's such a hot topic in mathematics. The exponential function e to the x is its own derivative. The derivative of e to the x is e to the x. It's really trippy, right? So, but yeah, so that property just has so many applications in mathematics. So for that reason, though, that's why we just kind of focus on it by itself. So f prime of x equals f of x. In other words, the derivative with respect to x of e to the x is e to the x. Okay, so that's one major properties. That's how we kind of introduce the derivative of the exponential function. Again, the takeaway here is that when the derivative of e to the x is itself. Okay, so find the derivative of y with respect to t. Maybe they meant for that to be the derivative of y with respect to x, because nobody has t. Yeah, I think they meant find dy by dx. Let me check. Yeah, I think looks like they meant dy by dx. Okay. Man, it's like full of errors today. It's one of them days. So I think that's supposed to right here. This is supposed to be I'll just cross out. Find dy by dx. Okay, I think that's what they meant to have. Okay. So then for part A, right? Dy by dx. So the derivative of y with respect to x. You could apply the product rule, right? Where you would say the first times the derivative of the second plus the second times the derivative of the first. But I think we had a property where the derivative of a constant times a function is just the constant times the constant times the derivative, right? So whichever one you resonate more with, I'm just going to use the shorter method here. So this derivative is going to be 3 times the derivative of the function, which is going to be itself, right? That should be it. Again, if you decided to use like the product rule, if you said the first times the derivative of the second, right, you'll get this plus the second times the derivative of the first, well, the derivative of a constant is 0. So that second term goes out and you're only left with the first term, which is this guy that you see in the box, okay? Now, I think part B, we definitely need to do the product rule, okay? Let me plug in my phone at least. Yeah. Anywho, I did pretty good today, though. I'm proud of myself. Like, I made sure the essential things were charged. My tablet, my pen, my keyboard. Normally, like, I'll be gaming up until the last minute, and then everything is drained. I'm like, crap. So I'm trying to charge while I like get things set up. But so I was like, no. I gave myself about an hour or two before the start of class. I was like, let me just plug stuff in so it'll be ready to go. Okay, so for part B, we want to do the product rule, right? So I'm going to put it here real quick. So the product rule, the first times the derivative of the second plus the second. This is our dy by dx. First times the second plus the second times the derivative of the first. Okay, so that's the product rule. Okay. So then for B, our dy by dx, the first, which is this guy, the derivative of the second, we're going to come back to that, second, which is this guy. The derivative d by dx of the first, which is this guy, okay? So then if we come back and do those calculations, the derivative of e to the x is itself. So the first expression becomes this. The derivative of x squared is 2x. So then that's going to be plus 2x e to the x, and I'm going to leave it like this. For the sake of space, I'm going to break that first line up, or I guess I could shrink it down. I'll just shrink it down. I was going to break it into 2 lines. I feel like it into a little bit better. I'm trying to leave some space for C. I know it's a little bit weird. But I still feel like I need to shrink it down some. Okay, we'll go with that. All right, so then part C, quotient rule, right? So I'll do this color. So d by dx. So I remember there's low d high minus high d low over low low. All right. Low d high minus high d low over low low. Okay. So then for C, dy by dx, the bottom, the derivative of the top is itself minus the top times the derivative of the bottom is going to be what? 3x squared over the bottom squared, x to the power of 6. Now it looks like all terms have at least 2 x's. And then we can also factor out an e to the x. So let me see. I'm going to factor out x squared e to the x. We're going to be left with x minus 3 over x to the 6. It's kind of an automatic extension already built in. Okay, let me, so let's do our cancellations. This guy is going to cancel 2 of these, so 4 are going to be left over. And then that's essentially our final result. E to the x, x minus 3 over x to the 4. Okay. All right, let's see how do we do. So for the first one, we got 3e to the x. Right there, 3e to the x. And then x squared e to the x plus 2x e to the x. That's fine. They factor out the e to the x squared. That's fine. We got the same thing. And then e to the x times x minus 3 over x to the 4. X minus 3 over x to the 4. Okay. All right. So let me see. So, okay, so we've introduced the derivative of e to the x. The unique property of e to the x is that it's its own derivative. So the derivative of e to the x is e to the x. So now we want to look at the derivative of e to the power of a function. And so essentially what we have to do here is apply the chain rule, right? So it's going to be the derivative of the outside function times the derivative of the inside function. But the derivative of the outside function is itself, so that's why it's showing up as e to the f of x, right? So again, from the chain rule, we would say the derivative of the outside function times the derivative of the inside function. And if you couple that with the fact that e is its own derivative, that's why that first part is e to the power of f of x, okay? Okay. So the derivative of e to some power is the product of e to that power and the derivative power. That's fine. Oh. All right, so differentiate each of the following. If you heard that pop, that was my ankle. Getting young in my old age. Differentiate each of the following with respect to x, okay? I'm still a fan of just doing the chain rule, derivative of the outside function times the derivative of the inside function. Again, the derivative of the outside function in part A is going to be itself, okay? So then, as we could say, dy by dx is going to be e to the 8x times, the inside function in this case is 8x. The derivative of 8x is just going to be an 8. So I'm just going to move it here in front. Okay. We'll work B here. Okay. So then our dy by dx is going to be itself, which is this, times the derivative of the inside function, negative 2x plus 4. I think I'm going to leave it like that. I'm going to, I kind of want to shrink it down. Okay, so we'll use that. And for part C, something similar. The derivative of y with respect to x, I'm going to break this and move into 2 lines. So it should be itself, which is this, square root of x squared minus 3 times the derivative of the inside function. I mean, it's like we have to do the chain rule twice here. So that square root, the 1/2 comes down. We're going to be left with x squared minus 3 to the power of a negative 1/2. But then we got to say times the derivative of the inside, the radicand basically, which is going to be a 2x. Okay. It looks like this 2 cancels this 1/2. Okay. So then ultimately it looks like we have x over the square root of x squared minus 3. Okay. Times e to the power of square root of x squared minus 3. Okay. So with that one, it may have helped if you like did the derivative of that radical off to the side, right? And that's where that whole x over square root of x came from. That may have been more simple to just do that off to the side and then multiply it by the original function. Okay, I feel like these are all good. Okay. Okay, so now we're asked to find the second derivative of y with respect to x for this function. In other words, take the derivative, whatever answer you get, take the derivative again. Okay, so let's give it a go. So first we're going to find the first derivative. So dy by dx. Let's see. So it should be itself times the derivative of the inside function, negative 10x. Right? Because the 2 comes down, you subtract 1. This is the result we get. Okay. So now for the second derivative, it looks like we have to apply the product rule. So the second derivative of y with respect to x is going to be what? The first, which is this guy, times the derivative of the second is just negative 10. So the first times the second plus the second, the derivative of the first, I think we just did it. So we got to basically just rewrite that. E to the negative 5x squared times negative 10. Right? Easy to get lost in the sauce. Just kind of take your time. Now it looks like we have some common expressions that we can factor out here. Looks like we can factor out a negative 10 e to the negative 5x squared, right? Like they both have this negative 10 and they have this. Again, we can take the negative 10 and this. So if we factor those out, looks like we'll have negative 10 e to the negative 5x squared. Now from that first expression, it looks like there is a 1 left over. Okay. I think it's a negative there, right? Because we had double negatives. We took out 1, so 1 persists. So it's going to be a negative. Looks like it's 10x squared. And I think that's it, really. Because we took out the e to the negative 5x squared. Okay, let's see how do we do. And negative 10 e to the negative 5x squared times 1 minus 10 minus x squared. Okay, that's dy by dx. Okay, that's fine. If we distribute the negative, it'll reverse the order. Did we get that? Mm-hmm. If we distribute the negative, we'll have 10x squared minus 1. 10x squared minus 1 is 5. Okay. I think that might be it. Oh, okay. Let's look at this example. So growth of an account. Franco's Fishing. You know what? This is so trippy. Franco's Fishing Emporium. So in Mobile Legends, the game I play, there's a character called Franco. He's a tank. And his ability is he throws out this hook, and it's always like fishing because you're trying to hook the opponent like in a fishing line. And so it's just weird that this example says Franco's Fishing Emporium, and you have this tank that people like, time to go fishing, you know? It's trippy. Anyway. Franco's Fishing Emporium invested $50,000 into an account that earns 1.25% annual interest compounded continuously. The value of the account after 2 years is given by this. Find the amount in the account after 5 years and a prime of 5 and interpret the remaining. The rate of change of, we'll look at it. Okay. For a of 5, it looks like we can just plug in, right? They gave us the model. So we just let t be 5. We get a result. Here, let's go here. Let's go to y equals. We got 50, 1, 2, 3 times e to the power of 0.0125x. Okay. I want to evaluate this function when x is what, 5. So after 5 years, $3,000. I mean, it grew, just for sitting there, but I want to get to some of those big numbers, right? Anyway. Okay, so the amount in the account after 5 years, we got approximately this one. So then 53,224 and 72 cents. Let's see. So A prime. Okay. So if we go to take the derivative of this guy, that 50,000 can just go in front. The derivative of E is itself times the derivative of the inside function. So really, we're just going to take this result and multiply it by the derivative of the inside function, which should just be the 0.0. So we can take that answer and say times the rate. 125. So again, for A prime, all I did was I said A of 5 times basically our R. So that's the rate of growth. That's how much the account is growing each year at that moment in time. And 31 cents per year. That's the rate of growth of the account each year in that moment in time. So again, essentially the first one was a calculator problem. And then when you go to calculate the derivative of the future amount, again, applying the properties, it ends up just being that the original function times the rate. If you do it manually, if you do the calculations manually, you'll see that the only thing that's going to be left is the original times the rate, and it should give you this. Okay, let me just check my numbers. And again, on the next slide, we have all this already worked out. If I can get it to work, what's the time? 2472. Okay. So again, the derivative of the function, the 50 can just go in front. The derivative of e is itself times the derivative of the inside function. The derivative of the inside function ends up just being the rate, again, by the chain rule. So then when you finish calculating, we get that this. So then after 5 years, the value of Franklin's fishing employment account is going to be $53,224.72. And at this instant, the value is growing at a rate of $665.31 per year. Okay. All right, so the derivative of the exponential function is itself. And then the derivative of an exponential function to the power of another function, you apply the chain rule, it's going to be itself times the derivative of that inside function. Okay. I feel like there should be questions, but again, I'm not going to pressure you. So today we were able to successfully get through sections 2.1 and 2.2. I want to say, the assignments are there. On your own, it's a good idea to try to go ahead and get through 2.3 and 2.4. So, obviously you want to do your best to go ahead and finish out 2.1 and 2.2. If you finish and you feel up to the task, go ahead and use my recordings. As far as this recording, I'll probably have to pull it and just load it to my channel. It just won't be live. I don't know why it wouldn't let me go live. It was saying I reached a limit, but this is the first year that it's saying anything about a limit. But anyway, you should be able to access this. So if you go into Zoom, like zoom.com, and you have to log into like your account using your Morehouse credentials, and you can find the recording there. But I'll try to put it on my YouTube channel where I have the others. So that's just homework I got to do, a little bit extra homework. But for sections 2.3 and 2.4, again, it's a good idea to go ahead and use my recordings and go ahead and do those assignments. Like try to finish it out before Wednesday's class. So that way Wednesday can be a review. And then once you finish all the stuff for this week, it doesn't hurt to go ahead and do the assignments for next week, right? And if you can at least stay like 1 week ahead of me, that's a good position to be in. If you feel up to the task, then you can finish out everything, and then you're just going to be waiting on the exams. We are approaching exam 1. It's basically 2 exams and a final. Exam 1 is going to cover chapters 1 and 2, right? So once we finish out chapter 2, then we'll be ready for exam 1. And then we'll start working on chapters 3 and 4. Once we finish chapter 4, we'll take exam 2, and then shortly thereafter, we'll take the final. Are there any burning questions before we go our separate ways? Going once, going twice.
I have a question. I'll stay after that stuff.
Okay. Any other questions? All right, gentlemen. So if there aren't any other burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy your evening, and we'll meet back on Wednesday, same time, same place.
Have a good one.
Thank you. Let me stop the recording. We can. Oh man, it might not have recorded. It definitely did recording in progress, and it seems like at some point it may have stopped. It's not even showing now. So I don't know. Yeah, usually I stream a live stream to YouTube, and somehow the settings are changed, and I think it's something with the administrators. So I don't know. So I don't even know if we have a recording of this one. We're gonna have to. That's why I have my other recordings. Okay, gentlemen. Who was the one that needed the private? Someone had a question. Are you still there? Okay, let me see. This one is Yeah, I mean that's fine. You know, you know how that stuff goes. Like, so whatever work you're doing is it's gonna save it. Just try to get access as soon as possible, and then so that way you don't get too far behind. Okay. All right, gentlemen. We'll take care. Mhm.